This is how I learned about the life cycle when I was in nursery school. We brought home eggs, they turned into tadpoles. We watched the tadpoles metamorphose into frogs. Does anybody have this experience? Do they still do this? I don't know, maybe it's cruel to frogs, and so they phased this out of elementary school science experiments. But the understanding that we get is that a life cycle consists of stages, and that a living organism like a frog goes through these discrete stages, and some of those include metamorphosis into a new stage that could not be predicted by watching the incremental stages of the previous stage. That is, if you look at the egg, it looks nothing like a frog. If you look at the tadpole, it looks nothing like the frog. And you wouldn't think, or you wouldn't know how to predict what the frog would look like merely from looking at the tadpole. So this is the ecological or biological life cycle. The next slide shows us a different type of life cycle. This is the product life cycle. And we're showing how the biological metaphor is now extended onto an industrial product. Here, the idea is that we invest in product development. So you can see the profits line dips down below the zero axis. This means that we're investing rather than making money. We introduce the product and now we have sales. Profits are the net of sales and costs of production. So after we reach a certain scale in this particular product, we start to make money off of it. But the product becomes obsolete and the sales decline. As each succeeding product supersedes the prior one, we see that the prior generation goes through a life cycle like this, where it grows almost exponentially in sales, peaks, and then declines. At the end of its life, the product essentially dies. This also happens at a larger scale, like companies. Right now, you could say, well, we don't know if BlackBerry is going to survive. BlackBerry went through an exponential growth phase. It's been superseded by competing companies, and now sales are in decline. The same thing happened to Blockbuster. The same thing has happened to other companies that undergo or manage poorly a technology transition. So this is the product life cycle, but it also applies at a larger scale, the scale of the company. We saw the biological and the economic. The next slide shows us one more. This is the materials life cycle. We're not focused on any particular product or any particular organism or any particular company, but here we're focused on materials. We extract materials from the environment. I've shown that in the red arrow. Natural resources go into these extractive processes. Mining is a good example. Fossil fuel extraction is a good example. These raw materials go into manufacturing. As they produce products, the products get shipped out to consumers. We follow around in a clockwise fashion from packaging and distribution to use and maintenance. Finally, when the consumer is done with the product, we reach disposal. I'm just following the blue circular curve around in the materials life cycle. And at disposal, a number of things can happen. The materials can be released into the environment. They can be recycled back into new products. They can be reused. Sometimes that's called downcycling by other users. Or they can be recovered through recycling processes that extract what's valuable inside the products and move them into a new materials life cycle. So these are the three different, on the next slide, I've juxtaposed the three different applications of the life cycle metaphor. Whereas biology is the original life cycle. Here, things really, they have a literal death. In the product life cycle, it's more of a virtual death, since the product was never alive to begin with. And then finally, the material life cycle. We know from the first law of thermodynamics that materials never die, but they can be dissipated back into the environment, or they can be lost from the economy. So I've put some questions up that ask us to compare these three different life cycles. I'm not going to ask you to do that right now. I'm going to keep moving through the presentation, but in reading the questions you can see that looking at the life cycle or applying the life cycle metaphor in these three different ways highlights some attributes and it shields other attributes from the way that we view the technologies represented in the product and the materials life cycle. Let's go to the next slide. One way that we examine large engineering projects is through life cycle costing. So here I'm taking either a product metaphor or a project metaphor. I've linearized what used to be a circular life cycle. So we're moving from the beginning, design, over to the end, demolition, taking the example of a building. Buildings are large complicated, although usually not complex structures. They're expensive. In the design stage, we spend very little money. That's represented by the dashed line. As design moves forward, we're paying architects, we're paying engineers. We spend money on design. We have a lot of control over how much money we're eventually going to spend. That's the solid black line, which is declining. If you don't ever start with the design, if you don't ever spend any money, you don't get any building. You don't even get any design. But you can save 100% of your costs. So at the onset of a project, at this idea stage, you have 100% control over your costs. As you make commitments in design, the constraints that you accept, the design choices that you make, how big will the building be, where will it be situated, this reduces the control that you have over your total costs during the design phase. Then we can see in construction, the bulk of the cost in buildings is in construction. We've lost all of the control over costs that are related to design. We now have a little bit of control, so the black line goes straight back up, over our construction costs. We can't save all of our project costs, but by doing things in acquisition, that is, by doing a good job of bidding out the building and selecting a contractor, we may be able to acquire the building at less cost, or if we do a poor job, more cost during construction. There may also be choices that we have to make during construction that can make the building more or less expensive. We accumulate costs on the dashed line, and our control over costs decline. Now we're in use. And in use, there's sort of this shark fin diagram on the dark line. This represents the continuous costs of operating the building. We're talking about electricity, maintenance, and every once in a while a renovation. And so the cost spike corresponds to a renovation. Finally, we have demolition, in which we complete the accumulation of our costs. You see the dashed line is all the way back up to 100. It's important to understand the life cycle costing. This is an application of the life cycle metaphor, because things that we do in the design stage are going to impact costs that we don't incur until we get to construction or use or demolition. The advantage of adopting the life cycle perspective is that we can see how the choices we make early constrain us later. This is an important application of the life cycle metaphor. Let's move on to the next slide. This is the materials life cycle that we saw earlier applied to a specific product. Here it's not just one material, it's all of the materials. I've chosen the example of a plastic bottle. So the plastic bottle must require primary resources. I've listed that at the top in resin manufacture. We go through all the stages of the plastic bottle and what can happen to the plastic bottle after use or after collection. And the way that the plastic bottle can be reused, refilled, recycled, or disposed of. If we're going to do environmental life cycle assessment rather than a financial, like life cycle costing, then we need to understand all of the material flows in the product life cycle diagram, particularly those materials that are released into the environment. When materials released into the environment, we typically call that pollution. Now sometimes we treat the material flow, sewage for example, and release back into the environment treated waste. Treated waste is less impactful and less polluting. So from an environmental perspective, we can add up all of the materials that are released into the environment, create an inventory of these, and try and get a sense of what the environmental impacts of that inventory are. I've listed that on the next slide. The way we do that is collect all of the emissions released into the environment. This might be a long list of 6,000 chemicals or substances, and relate them to different environmental impact. Here I've listed them as midpoint impact categories, things about the environment that we care about. So smog formation, acidification, global warming, and on down the list, including human health impacts. Each one of these emissions may impact the environment in a way that we care. So we aggregate them all in relation to the impacts that they have. Hit the button for some animation. For example, global warming is not the cause of just one gas. Carbon dioxide is one of the most important, but it is caused by a multitude of gases. In order to express all of their global warming impacts, we use a characterization factor. We take methane, we take NO2, we'll take hydrofluorocarbons. All of these cause, or they trap infrared radiation, which causes global warming. We can relate them all to CO2. We say that one substance is more or nothing is really less potent than CO2 except water vapor, but we relate them to how potent they are compared to CO2. So a global warming potential of 20, which might be typical for methane, tells you that it's 20 times more impactful, 20 times more powerful a greenhouse gas than CO2. Each one of these characterization factors, in this case global warming potentials, we multiply that by the mass of emission released into the environment to get an aggregated understanding of what the global warming, expressed in CO2 equivalents, midpoint impact will be. We do this for all of the categories. Now we have sort of a simpler, not simplistic, but simpler accounting of what the environmental consequences of the bottle life cycle are. So I've shown you life cycle costing and environmental life cycle assessment. Let's move to the next slide. You're going to have to move through this one too to pull some animation, but I want to show an example of life cycle assessment. This is just for NOx emissions. People say that photovoltaics are clean power, and that's true in the use phase. But in manufacturing, it takes electricity to make photovoltaics. Does that make sense? There are certainly emissions associated with that electricity. So go ahead and hit the button. Let's see what we got. The multi-crystalline silicon versus the CAD-TEL each embody in their life cycle different NOx emissions per kilowatt hour generated. The multicrystalline silicon are fairly high, about 65 milligrams per kilowatt hour, and comparatively the CAD-TEL are about half. So if the CAD-TEL is longer lasting or produces more power, or in this case more energy, kilowatt hours, then the emissions that were used in the manufacturing phase are going to be divided by a larger number. And this would make the milligrams per kilowatt hour look more favorable. So this looks at all of the life cycle stages, but relative to what the purpose of the product is. The purpose of the product is expressed here in kilowatt hours. That's called the functional unit. So the functional unit is why people want the product to begin with. Now you could say kilowatt hours aren't the functional unit. Nobody actually wants electricity. I mean, you don't put electricity in your pocket. You don't treasure electricity. You only want the electricity because of what it does for you. You want light, or you want communications, or you want, I don't know, to run fans or air conditioning. But in this case, we've chosen the functional unit as the kilowatt hours, the energy produced over the lifetime of the module, and you can see that this ratio might be impacted by the milligrams of NOx released during manufacturing, or it might be impacted by the electricity produced during life. Terrific. Let's go to the next slide. I think we're mastering the life cycle perspective here. Here, another linearized life cycle diagram, life cycle greenhouse gas emissions for petroleum fuels. And what we've shown are all the different stages from extraction of the petroleum to production of gasoline. That's nice. Let's advance through this. Just to show you that the life cycle perspective is robust. We can apply it to lots of different products. Here we're doing the same thing, life cycle greenhouse gas emissions, and this is different photovoltaic technologies. It's probably hard for you in the audience to read this, but we have monocrystalline silicon. I'm reading from the second column over. Polyamorphous, CAD-TEL, nanocrystalline dye-sensitized, the concentrator, ribbon silicon, etc. And again, the CAD-TEL performs extremely well relative to the silicon technologies. Amorphous silicon, though, has a much lower expected life cycle greenhouse gas emissions profile than the polycrystalline or the monocrystalline. Different look at it, life cycle greenhouse gas emissions of renewable energy and technologies. In the use phase, coal and oil produce a lot of CO2 because they're carbon-intensive fuels. They're listed at the right-hand side. Lots of greenhouse gas emissions when you're using those fuels to generate electricity. Over on the left-hand side, we have biofuels, photovoltaics, concentrating solar power, geothermal energy, etc., etc. And yes, by and large, the renewables are less impactful on a life cycle basis when it comes to greenhouse gas emissions than the fossil fuels. This is one of the reasons that we're attracted, one of the environmental reasons why we're attracted to renewable energy. Let's go to the next slide. Just keep going. So here we have an interesting look at coal. What we want to know is how much land. The previous slide asked, what are the greenhouse gas emissions over the life cycle? But here is a different question. How much land does it take when we're comparing energy technologies for producing electricity over the total sort of footprint? This includes transmission, this includes extraction, so this is everything that delivers the electricity to its final use. And we see that not all coal is created equal. Coal underground doesn't consume a lot of land. Biomass, all the way on the right, this is biomass willow gasification in New York, consumes a great deal of land. The question is, where's PV? PV shows up about in the middle. It depends on whether it's rooftop, in which case it's extremely low, or whether it's a dedicated, as we have out in Gila Bend, dedicated, no, that's not, sorry, photovoltaic, but dedicated utility scale occupying its own land. The interesting thing to pull away from this graph is that PV doesn't occupy any more land than coal does, especially if it's integrated in rooftops, which makes sense. PV occupies less land than, for example, wind in Germany or wind in California. And what's really interesting is look at hydroelectric reservoirs in Colorado. They take up a lot of land. One of the objections that's often levied at photovoltaic technologies is that they occupy too much land. But compared with all other technologies, it's not necessarily the case when we take this life cycle perspective. Let's go to the next slide. Oh, actually, we're going to see a little animation pop up here. There we see the coal, the photovoltaics, and the hydro. Keep going. How could rooftop PV be so less impactful? Is because we're not occupying land when we put the PV over a parking lot or over a rooftop.